Well, good evening. Welcome everybody to Trinity College for this lecture with a most exciting title, a title that has attracted many people to come here on this wet November day. Cosmic Rays, a Century of Adventure and Mysteries. Every second year, the Dublin Institute of Advanced Studies holds a public lecture here in Trinity, with lectures in UCD in alternate years. In reflecting a little bit on what I would say, I just restate a little bit perhaps what some of you know. The Dublin Institute of Advanced Studies has three constituent schools: Celtic Studies, Theoretical Physics and Cosmic Physics. And if those three seem like an unusual mix, they harken back, I think, to the dual interests of the Institute's founder, Eamon de Valera, who was Taoiseach and president for decades. In many ways, Eamon de Valera was a divisive figure, as indeed are most political figures, I suppose. But equally, in some of his actions, he has proved a uniting, inspirational figure. And I think that this is nowhere more the case than in his founding and advocacy for the Dublin Institute of Advanced Studies, which is modelled on the Institute of Advanced Studies in Princeton. And at the time this institute was founded, in the 1940s, Ireland did not enjoy significant wealth. And some criticised Eamon de Valera at the time for using scarce resources to develop what they saw as an esoteric and unnecessary initiative. But Eamon de Valera understood the importance of promoting cutting-edge science and research. And indeed, in doing so, he created an institute prestigious enough to attract this man, Erwin Schrödinger, to come to Ireland. Now, those of you who know the history of Erwin Schrödinger will know that he was a Nobel Prize winner and helped establish this institute as a world-class research centre. And in 1943, he gave a public lecture entitled "What is Life?" And this lecture has claims to being one of the most significant lectures ever delivered in the world, and certainly delivered in Dublin, here in Dublin, our capital city. And it featured in Time magazine and was cited by Watson and Crick as an inspiration for their own work in unravelling the structure of DNA. Indeed, of course, the theatre we're in this evening is named after Schrödinger, which makes it an apt venue for tonight's lecture. When I talk about Eamon de Valera and Schrödinger in the same breath, of course, they weren't well matched in many respects, didn't have the same worldview perhaps, but they had the same worldview when it came to one thing, the question of quality and excellence. And you do what it takes to get quality and excellence, because excellence breeds excellence and leaves an enduring legacy. And the Dublin Institute of Advanced Studies is now a key component of the Irish research infrastructure, which has indeed developed the vision of its founders. It plays a crucial role in disseminating science knowledge to the public, and it has partnered with other institutions, including Trinity, on important initiatives. 3 weeks ago, it was announced as one of the partners in the forthcoming Centre for Research in Applied Geosciences, or ICRAG. And Professor Luke Drury, who introduced me here, and of course is director of the Institute's School of Cosmic Physics, is currently chair of the European Space Agency's Working Group on Astronomy. Now, it's of course an auspicious day for the European Space Agency. Yesterday, the team in charge of the Rosetta mission made history when it landed a robotic spacecraft on the comet. Probably not all just down to the physicists. As an engineer myself, I'd like to take most of the credit for that. And if any of you are interested in knowing the significance and implications of this landing, well, you're lucky, because here, I'm sure in this room, are people who can explain it to you. Tonight's talk is given by an international luminary in this field, Professor Etienne Parizot from the Université Paris 7. He has a special connection with the Dublin Institute of Advanced Studies because he was a postdoc researcher here for 2 years, until the year 2000, working under Professor Luke Drury on the European TMR network in astroplasma physics. Since then, he has become a noted science commentator. His TED talk on the 4 dimensions went viral in France, which is becoming an increasing benchmark of success, at least in the public outreach, and it augurs well for how we'll be entertained this evening. He is a member of the Pierre Auger Observatory, which has transformed our view of cosmic rays. He is currently making the case for sending a successor space mission, GEM Yuso, if that's how you pronounce it, to observe from the Japanese experimental module on the International Space Station. In tonight's talk, he will explain the need for such a mission, and he'll also be outlining the historical development of the field of cosmic rays. Ladies and gentlemen, Etienne Parizot.
Thank you very much. I'm very pleased indeed to be here. This room is really fascinating. The name of this room is even more fascinating. And I'm very happy to be back to Dublin. Indeed, I spent 2 years here working with Luke Drury. It was really, really nice. So I'm also delighted to talk about cosmic rays tonight because cosmic rays, as I wrote here, is one of the most interesting subjects in modern astrophysics. And it's largely unknown. And it's unknown by the public, which is a pity. The reason is maybe that there's no nice pictures to show. People like to think about astrophysics in terms of nice pictures. There are beautiful things from the cosmos. I won't show you nice pictures tonight because cosmic rays don't give rise to nice pictures, and it's an interesting thing, which I will emphasize. But these cosmic rays are very relevant, not only for astrophysicists, but also for the public. So let me nevertheless show you some nice pictures to start. There would be, you see here, emeralds and aquamarine. There would be none of these without cosmic rays. The color of this emerald comes from the beryllium element. Every beryllium atom in the universe has been once a cosmic ray or been made by a cosmic ray. There would be no emerald without cosmic rays. So you see it's important. Anyway, so cosmic rays is related to many, many things. There are a few pictures here related to species evolution, to the Eiffel Tower also. I will say a word about that. So this is a Chinese astronomical map of year 393. You have a Stradivarius over there. I come into some of this, not all of this, but just to tell you, cosmic rays do matter also to us on ground. So it's largely unknown by the public, but it's also largely unknown by many astrophysicists, which is not just a pity, it's a mistake, I think, maybe a fault, because it's a very significant phenomenon which plays a major role in what I like to call the galactic ecology. And well, they have also, these cosmic rays have played a very important role in the development of physical science. I will say a word about that too. Okay, so maybe you have never, if you already heard about cosmic rays, I think you have privileged persons. If you have not, then you will be a privileged person in a few minutes, so be happy. So 100 years after their discovery in 1912, it's time to remedy to this problem. So it's been mentioned that the astrophysics and geophysics department here is called the School of Cosmic Physics. This is not astrophysics, cosmic physics. It's a difference. Astra refers to stars. There's the word in French, astre, means earth. I think it's the English. It's something hot which is radiating, like a star, which radiates because it's hot. And it's radiate photons. And we've done indeed astronomy with starlight for 40,000 years and maybe more. What I'm going to talk about is something different. Light, of course, is a powerful tool to study the cosmos, and it's the cosmic messenger par excellence, but it's not the only one. So what are the cosmic rays? Let me say that straight away. These are high-energy particles which are going across the galaxy in all directions. They fill the galaxy. They even go beyond the galaxy. They fill the extragalactic space. They are mostly protons, but also other atomic nuclei. They are energetic. and they have a very wide range of energy. And from time to time, they encounter the atmosphere of the Earth, and they interact there. So the Earth's atmosphere protects us somehow from this radiation. And this produces secondary particles which can make it to the ground, and we can detect them. Okay, so it's a long story. It will take us from 1912, from this balloon flight, to this is Victor Hess, who got the Nobel Prize for his discovery of the cosmic rays thanks to this balloon flight, up to now, essentially, and maybe a bit later, I hope, to this other balloon flight, of which you saw some preliminary images just before the start. This flight took place on these dates, so less than 3 months ago. The first one gave a Nobel Prize to the guy. The second one won't give a Nobel Prize to anyone, but I was happy enough to be part of it. So that's why I'm going to talk about it. So, and then I hope we can go even beyond to space, to the International Space Station. I say a word about it at the end. So this story has a very special actor, which is this device, very simple thing called an electroscope. I have to explain this very briefly. Probably most of you have seen electroscopes, or maybe not. It doesn't matter. Electroscope is just some metallic arms like that which can move. And if you put charges, so this is the way it looks when it's unsharp. If you put charges, electric charges there, the charges will repel each other and do something like that. Then if you touch it, the charges go away from your body, which conducts charge to the ground, whatever. And so it will discharge and go back to this position. This is a very simple device, which was used long ago. And back in 1785, Coulomb, the French, I'm sorry, who did a lot for understanding the electrostatic force, noted that this electroscope discharged spontaneously, which should not be the case because the air is an insulator. Yeah, insulator? Okay. The air is an insulator, which is fortunate, otherwise we would, just approaching a plug would be, okay? So it's an insulator, so the charge cannot be removed. So once charged, the electroscope should remain like that. But Coulomb noticed that it does discharge slowly but surely, and this could not understand. Faraday also confirmed this information, and this, maybe we could claim it's actually the real discovery of cosmic rays. So let me just say two things about the scientific context. There are essentially two aspects in the physical world, light and matter, right? And there have been two major breakthroughs during the 19th century, both on the light and the matter side. Concerning light, as most of you probably know, 19th century has seen the unification of electric and magnetic phenomena, with these guys playing key roles, and the identification of the nature of light, which has been recognized to be an electromagnetic wave. And as far as matter is concerned, you probably know also that 19th century have seen the rejuvenation of the primitive atomic theory through chemistry studies, and it was recognized that the diversity of matter is in fact the result of combination of different atoms, unbreakable things, which are not so many. So the diversity of matter is just different combinations of those. At that time, nuclei and electrons, which I will talk slightly about, were completely unknown. And then some very interesting piece of equipment, very simple thing, was invented. This is, well, in 1985, Gensler invented the vacuum pump, thanks to which it was possible to create glass tubes with almost vacuum inside, and then you could put high voltage here, and that would produce some rays, some energetic particles would go out of here and just cross the thing, accelerated by the field. And this is how these rays were identified at the end of 19th century to be electrons. So, and the key point is that these electrons were realized to be 2,000 times smaller than the lightest of the nuclei. So, of the atoms. Atoms are supposed to be unbreakable, the smallest pieces, and yet this is 2,000 times less massive than the smallest atom. So this is the onset of subatomic physics, which is what is going to concern us now. So it's quite funny to see how deep one can go with such a simple instrument, and it's very funny to look at these pictures, you know, this hieroglyph. This has been debunked. And these are real things that you find on the, I don't know where in Egypt, but they are not. They look so much the same. But it looks even like you put the high voltage here, and here goes the electron. The reason I put this is because the way we discover the electrons, not we, I mean these guys, is because you know they are charged because they are bent like these snakes. They don't go straight because if you put some magnetic field, the charged particles just get bent. And this will be crucial for what comes. So just keep this picture in mind and you know what it's about. So there was a decade which completely revolutionized science at the end of the 19th century. I already mentioned the identification of these cathode rays produced by the cathode in this tube in 1897 was preceded just by 2 years by the discovery of X-rays. X means unknown. It was unknown until quite a long time after that. So these are really new things which are discovered, and each time people were wondering, is it light or is it matter? It's not, it was not clear. So cathode rays were identified to be matter, if you like, electrons. X-rays, it took this amount of time to discover this actually energetic photons. This is light. Then 1 year later was discovered the radioactivity, and then during the next few years it was realized there were different types of radioactivity. So what is it? Is it light? Is it matter? Actually, alpha radioactivity is matter. This is matter too, and this is light. But it took many years to figure out. So essentially, there were radiations emerging out of the infinitely small, but with very large energies, and which you could detect by induced effects like chemical reactions, atomic transition, and ionization. I come back to that. So once this had been discovered 100 years after the observation by Coulomb of the spontaneous discharge of these little things, it became clear that probably the reason for this spontaneous discharge is that there are some radiation which manage to ionize the air, which is an insulator. But if you ionize, what does it mean? It means you get some electrons out of the atoms, the molecules, and then it becomes charged. And then you have charge which are free in the air, which can carry away, compensate for the charges and just discharge the electroscope. So the reason why this discharges spontaneously is that there is some radiation somewhere which produces ionization and leads to this discharge. And this is quite nice because then, of course, the discharge is all the more rapid that the irradiation is intense. It's more intense. So it even becomes a measurement, a way to measure the intensity of radiation, right? So then people, of course, study these things. What can cause this? What is the source of the radiation? And for instance, Wilson noticed in the early 20th century that radiation was roughly as strong inside, just very deep in the ground. It was understood that, in fact, the main source of radiation is natural radioactivity. Radioactivity had just been discovered, and then we discovered that the rocks are radioactive by themselves. So they produce radiation which will ionize the things around and produce this spontaneous discharge of the electroscopes. And in 1909, Theodor Wolff, a very talented Jesuit physicist who made the best electroscopes in the world, was working along at the Eiffel Tower. There was a laboratory there that tried to make use of this huge thing that people wanted to get rid of. Anyway, and so the idea is very simple. We know some radiation, like if you put some uranium mineral, you will intensify the radiation. But you can also see the attenuation of the radiation when you propagate through air. Air will absorb some radiation. And you know how much the radiation decreases when you go 100 meters away, and so on and so on. So it was easy to compute if the radiation came from the rock, from the crust, from natural radioactivity. It would be easy to compute how much radiation would remain very high at the top of the Eiffel Tower, 320 meters. And you could compute the irradiation rate you expect. And so Theodor Wolff was working with an instrument here, and then he went up and down and to eliminate all sources of error. And he noticed that the remaining radiation up there was, smaller than what it is on the ground, but not as small as it should be. And it started to be quite puzzling. People were wondering, and some dared to go to balloon flights to go even higher to see what happens with this radiation. Can we get rid of it by getting away from the crust? And the reasons seem to be in agreement with the general idea that the continental crust radioactivity was responsible for this spontaneous discharge. But it was not so clear. The results were put into question. Other people went up to 3,000 meters in balloon in this year, and it seemed was not totally compatible with the dominant idea. Another guy, an Italian, had a very clever idea. There's another way to go far from the crust. Is to go in the middle of the lake or on the sea, right? And this is what he did. So this was, around these years, and the conclusion were quite clear. So he both worked below the water and then above the water, but in the middle of the lake where you are just far from the crust. And his conclusion is that the ionizing rays, whatever they are, nobody knows what they are, but whatever they are, they do not come from the crust. Okay, and so, is there something in the air? So people wanted to know better, and this guy was probably the most fearless physicist at that time. And so he went for a series of flights between 1911 and 1912. The idea is that he would just bring an electroscope with him, and going higher and higher, it would measure the spontaneous discharge rate, how quickly it would discharge because of the ionization from some rays, whatever they are. And so he would make stops at different altitudes and just measure the intensity of radiation. And this is what he found. Before that, this is the flight. So he took off very early. I don't understand why people have to get up so early. Maybe that's the way you get a Nobel Prize. So I gave up on that very early. Anyway, so it reached a maximum altitude. This is what I wanted to show you, of 5,000 meters. So it was dressed like that with no oxygen and so on. I don't know. I actually went in such a balloon. How do you call this thing where you basket? It's amazing. It's just amazing. There were 3 people there: one meteorologist and one also engineer. It's just amazing, and they went up to 5,000 meters. So anyway, and then landed in Brandenburg around noon. It's about the time when I would have taken off. Anyway. And this is what he measured. This is very, very impressive. So this is altitude, and the higher you go. So in the beginning, and this is the intensity of the radiation. So it's in French here. So when you go up, the radiation goes a bit less, like in the top of the Eiffel Tower. But then, if you go higher and higher, then it becomes more and more intense. It's just completely obvious here. The higher you go, the more you have. And it actually comes from the cosmos. That's the conclusion. And as made the right conclusion, these cosmic rays come from the cosmos. These particles, these rays come from the cosmos, right? Okay, so, but what is it? Is it light? Is it matter? Always the same question. You discover new things, and you just don't know what it is. And so, from the discovery in 1912 to 1929, was really confused. Robert Millikan thought that these rays discovered by Hess are actually gamma rays, which means very energetic photons, and he gave the name cosmic rays. But in fact, it's difficult to really make experiments with these particles, because we don't know the particles, but we don't have detectors as well. It's just the beginning of this particle physics. And so, anyway, in 1929, Bode and Coderster worked with what we call Geiger detectors. And if these particles trigger Geiger counters, they have to be charged, so not light, not photons. And also, it was found that a magnetic field applied to these particles would bend the trajectories, which is another proof that it's charged. But you know, Robert Millikan had the Nobel Prize. He says it's photons. It has to be photons, even if... So he needed another Nobel Prize to be proven wrong, actually. This other Nobel Prize is Compton, who studied... So the reasoning is the following. Because actually, Robert Millikan is not just a stupid guy, obviously. He's a very clever guy. He said, okay, possibly the particles that you see on the ground, they are curved by magnetic field, so they are charged, so it's not light. But these are not the real cosmic rays. The real cosmic rays are not the particles we see there. What we see is the secondary particles produced by the interaction of the cosmic rays in the atmosphere. What about the real cosmic rays, the ones which are in the cosmos? Maybe they are indeed photons, and then they produce charged particles by interacting in the atmosphere. The way to know is to try to bend the trajectory of the particles up there, but in these days you won't go in space to measure them. But the Earth produces a magnetic field, so why not use the Earth's magnetic field to see if the Earth's magnetic field can bend these particles before they reach the atmosphere, while they are still cosmic rays? And this is what was done. The idea is that if they are charged, there would be an effect that would make a different flux around the poles and around the equator, which is the reason why you have northern lights around the poles, because particles are guided there, right? And so it was a huge effort with 60 researchers sent all over the world to measure the flux of these cosmic rays at different latitudes. And the answer was clear. The cosmic rays, even before reaching the atmosphere, are charged, so they are not light. So we know what they are, and so people started to study these particles, which are very energetic. And so, in fact, particle physics was born from the study of cosmic rays. So I won't have time to go much into this, although it's extremely interesting. But just to mention a few key dates. In 1930, Paul Dirac had predicted antimatter. And antimatter was discovered 2 years later in a track in one of the detectors produced by a cosmic ray. And so discovery of antimatter comes from cosmic ray. This is another Nobel Prize associated with cosmic rays. Then, this is interesting to show. In the coming years, like in the 30s, particles were studying kind of, let me just keep this and go to that. What happens here? So this is a device which allows to record the track of an energetic particle. No, does not matter how. What you see here, you have energetic particles which comes in, and you see the track, one particle here. And here is lead, very heavy, so the particles will interact with that. In this interaction, because it's very energetic, it will produce many secondary particles that you see here, many different ones. And then another layer of lead. So these secondary particles will interact again and produce again several more particles, and so on and so on. You have a whole shower, it's called a particle shower, which can develop. One very energetic particle will just convert its energy into many less energetic particles. This multiple conversion of the initial energy. So remember this particle shower. Then there was discovery of muon. Okay, I should skip that. Well, just this summary. From cosmic rays, we were able, physicists at that time were able to really give birth to particle physics. I mentioned discovery of positron, antimatter. There are many particles, strange particles you may have heard about, which were strange because they have a lifetime which is much too long for their mass. And then it was discovered they have a special quark in them, but much later, which is called now the strange quark for this reason. So all this particle physics was born with cosmic rays, but we still don't, at that time, we still don't know what cosmic rays really are. what is their nature, and where do they come from? So what about the cosmic rays themselves? So we know they are charged particles. We know there are positive charged particles from east-west effect around the Earth. These are details. We know they are mostly protons. And this by itself is a major revolution. As I said, for 40,000 years we've been doing astronomy with photons, with light, which has been the only messenger from the cosmos. And now there's a new type of messenger that comes from the cosmos, and it's matter, right? So some researchers have understood that the cosmic rays were also very interesting for themselves, and so the question that you may ask is, what are the primary particles before entering the atmosphere? What are their characteristics, their energy distribution, their composition, which nuclei? Where do they come from? How do they get their energy? Because they're very energetic. What in the universe makes them? And can they teach us something about the cosmos that light cannot teach us? What is their influence in various processes occurring in the universe? And can one actually use these new particles to do astrophysics in a different way, to collect new messages? So there was kind of a schism or scission, I don't know, in 1953 at the time when it became, terrestrial particle accelerators became mature enough that we didn't have to wait for a cosmic ray to come and make an interaction to study them. If you can produce yourself your beam of energetic particles, it's obviously better. So people who were interested in particle physics for particle physics itself start to consider cosmic rays. They went to accelerator physics. But some other people consider that cosmic rays are interesting for themselves. Among them, Pierre Auger, which I will mention a little bit later. So let me go quick on that. Cosmic rays are really extraterrestrial matter that comes to us with a flux of about 4 cosmic rays per square centimeter per second arrive on Earth. So if you multiply by the surface of the Earth and you integrate over 1 year, you find that the Earth gets heavier by about 1 kilogram per year from extraterrestrial matter, which is much, much less than the 40,000 tons per year that comes from meteorites. But meteorites don't come from far. These cosmic rays can come from the other side of the galaxy, and even for some of them, the most energetic of them, from other galaxies, which is quite fascinating, right? So, but the big novelty is that something comes from cosmos which is not light, and this should give rise to a new astronomy, which is not just photon astronomy in different wavelengths, like you've heard about gamma rays, X-rays, radio waves. This is very nice, but it's still photons. Here I'm talking about completely new astronomy, matter astronomy. Just very quickly to say that cosmic rays, because I won't have time to explain this, I want to concentrate on something else, but I really want to emphasize that the cosmic rays play a very central role in most of the key galactic processes. They are one of the main components of the galaxies, actually, in terms of energy densities. There's as much energy in the cosmic rays in the galaxy than in light, right? So it's very important, and they control the ionization of the interstellar medium. Just as they ionize the air here, that's how they were discovered, they ionize the interstellar medium, and this has a lot of important implications. They're responsible for the heating of the interstellar medium. They are responsible for the generation of turbulent magnetic field. They also control astrochemistry, the building of complex or elaborated chemical components in the interstellar medium, like amino acids and things like that. They also play an important role in the regulation of star formation, which is obviously something important for a galaxy. They're also responsible for the nucleosynthesis, so the production of 3 very important nuclei: lithium, beryllium, and boron. I mentioned the emerald at the beginning. It's just one example. They also play a role in the evolution of species, and because they are a source of radiation which can trigger some diversity bursts in the species. There are observations which are quite interesting. They may have an impact on climate and so on. Anyway, this is very universal phenomenon which is still very poorly known. And the reason why it's poorly known is that I mentioned it's a new astronomy. The point is that it's new, that's for sure. It's not photons, it's really matter. But it's not an astronomy because you cannot do pointing with the cosmic rays. When you see a star somewhere here, well, you see the light coming from the star, but you know the star is just behind the light. It just goes straight. But the cosmic rays are charged particles. And as you know, if you remember this Egyptian picture, the charged particles with the magnetic field are bending. So they are deflected. So actually what happens is, okay, here is a computation that I could have drawn it by hand, or your dog could have drawn it. This is the trajectory of a cosmic ray in the galaxy influenced by the magnetic field. So it goes in all directions, completely isotropized, which means that if you see a cosmic ray coming from here, maybe its source is here, or here, or here, or anywhere. It could be anywhere. You don't see the sources because the cosmic rays are completely isotropized. Anywhere you look in the sky, you see the same thing. So that's why you don't know we don't know the sources because we don't see them. So we have to find other ways. It's an astronomy which is a bit complicated. So in fact, the cosmic rays are cosmic, yes, but they are not rays in the sense that a ray is something that comes from the center and goes away. I don't know how you call this in English. This is called a ray in French. A spore? Ah, okay. In French, it's called a ray. It starts from the center and goes straight, like the sun. Well, this is the sun. Sorry. Anyway, so they are not. The photons are rays really because they. Oh, oops! I just. Anyway, the cosmic rays are not rays. They are isotropized, so there's a complete blurring of the sky. So how to understand this phenomenon? So you see, this is an example. These are rays, sun rays. Even if you don't see the sun, you know where it is. You just go straight from the ray. You know where it is. For cosmic rays, this is what you have. You're in the mist. This is magnetic mist, really. So the next picture is a high-resolution picture of the sky in cosmic rays. Here it is. This is completely uniform. Anywhere you look, it's the same flux, completely isotropized. That's the way it is. So how do we go out, or how do we break, I don't know how to say in English, the magnetic mist? There are two ways. One way is to, well, essentially you want to transform the cosmic rays into rays. So one way is to transform, well, if the energetic particles interact with the ambient matter, wherever they are, they will interact with the matter and produce some secondary photons or neutrinos, which then go straight, and then you would see the interaction place. You would see that the cosmic rays is over there, or energetic particle is over there, because there it has interacted, produced some photon, and then the photon comes straight. That's a way. That's still standard astronomy. You see photons. This is very important. Most of essentially all the high energy astrophysics which is done nowadays is done from the secondary light emitted by the cosmic rays. But there's another way which is quite interesting, and I will go into that. The point is that the problem, again, of cosmic rays is that they are deflected by the magnetic field. But the higher the energy, the smaller the deflection, which is quite easy to understand. Okay? If the cosmic ray is more energetic, it will be harder to bend. So the magnetic field will have less effect on high energy cosmic rays. So if we could look for very high energy cosmic rays, maybe there's a way to break the magnetic mist and start to see sources behind the arrival direction of these particles. So I have to go back in time to this moment, 1938, and to this guy which I mentioned before, Pierre Auger. The French again, I'm sorry. So Pierre Auger noticed some coincidental detection of cosmic rays. So what I represented here is just some detector. However it works, it's some detector. Let's say each time a cosmic ray comes, it does something like that, you know. And Pierre Auger noticed that from time to time there would be coincidental detection of two detectors which are not at the same place, as if there were two cosmic rays arriving exactly at the same time. So you might say, okay, in fact, what happens is that there's one cosmic ray which crosses like that. Okay, yeah, because they go at the speed of light almost. So yeah, it could be that. So then it's a little bit clearer. You put something on top, and then you can know that it's come indeed from above. But you still see this kind of coincidences. Then you can study the distribution of the cosmic rays which arrive all at the same time by putting several detectors, and you still have these coincidences. This is quite strange. And you can even separate the detectors further and further, and less often, but still from time to time, you would see coincident detection. And what Pierre Auger understood is that what he was seeing is actually an atmospheric shower. It's a cosmic, if you remember the picture I showed you with these energetic particles coming here, interacting and producing many secondary particles. This, Pierre Auger understood, is exactly what's happening in the atmosphere. You have a very energetic cosmic ray that comes in, and it interacts, produces secondary particles. Each of them is energetic enough to produce more and more and more. And you have a whole shower of particles, it's called a shower, which can cover a large area and trigger detectors over a large area. And this is the reason for the coincidence. So that's quite interesting. And now the really stupefying, whatever, the amazing thing is that using the distribution of the particles over a large area, you can reconstruct the energy of the incident particle. You just add up the energy of all these secondary particles, which you detect in many places. You just sum all this, and you have the energy of the incoming particle. It could even be higher, but at least the energy of the incoming particle is whatever, it's the sum of what you have measured. And when you do that, so this is what he actually wrote in the Académie des Sciences report. It's in French, never mind. The bottom line, I didn't want to translate, but maybe some of you can read that. But anyway, he explains how he was able to evaluate the energy. The conclusion is important. The energy of these particles is larger than 10 to the 15 electron volts. Let me explain that. That's 1 million of billion of an electron volt. Electron volt is some energy unit that we use in high energy physics. Essentially, it's the energy of a photon of visible light. So it's standard energy, right? But this is a million billion times larger. Even today in LHC, in CERN, the biggest particle accelerator, you reach only a hundredth of that. So it's just a huge energy. Nobody could imagine that something like that would exist in the universe, yet it's the case. Now, up to which energy does it go? If you want to measure higher energy particles, you want to try to detect coincidences over a very, very large area, and larger and larger. The problem is that the higher you go in energy, so the larger the spacing of your detectors, the longer it takes to have a coincidence, because there are fewer and fewer particles at higher and higher energy. So if you separate detectors by 5 meters, you have to wait for 40 minutes. By 20 meters, you have to wait for more than 1 hour. If you were to separate the detectors by 1 kilometer, you would have to wait for years to detect them. So up to which energy does it go? Now, this is the only real physics that I will say. These particles, just to make you sense what it is, these particles are so energetic that, so energetic means so rapidly moving, almost at the speed of light, that they are subject to space-time effects known since Albert Einstein from the theory of relativity. These are called time dilation and length contraction. The only thing you have to know is that space-time plays tricks with our intuition, and time and space are relative. The duration of a phenomenon depends on the speed, depends on the race, on the speed of the measuring device, if you like. And there's one factor, called the Lorentz factor, which is essentially just a number that measures the strength of these relativistic effects, how much the space-time is affected by the very high speed of these particles. And I just want to give you these very simple estimates. At low velocity, Lorentz factor, this measurement of the strength of relativistic effect, is 1. Means nothing changes. 1 is normal. No relativistic effect. When you reach half of the speed of light, which is huge already, okay, Lorentz factor is just 1.15, so let's say 15% effect. If you reach 3/4 of the speed of light, 1.5. If you reach 90% of the speed of light, then 2.29. At 99% of the speed of light, you have an effect which is a factor of 7, which is a large effect. Now the particles that Pierre Roger has detected have a Lorentz factor of 1 million. And to give you an idea of this space-time effect, 1 second in the proper time of these particles, for themselves, when 1 second is spent, 3 weeks of our time has gone. You see, so this is time distortion. And for space distortion, 1 kilometer here, from here to wherever, Dublin Institute for Advanced Studies, 1 kilometer would be 1 millimeter in the race frame of this particle. This is really a huge space-time effect. Anyway, so these particles are so energetic that we start to think that we can indeed do particle astronomy and break the magnetic mist, because here is a picture of what you have. If you propagate particles in the galactic magnetic field, at low energy you have that, which is our problem. You don't see the sources, everything is isotropized. If you increase the energy, it starts to be less and less bent, and at some point it simply goes almost straight. And then you would start to see the sources behind the mist. You would start to do astronomy. This is the idea. Now, so from that time began a quest for the very, very highest energy particles. And you saw, starting from the 1940s, people developing arrays of detectors like that, covering huge surfaces to find coincidences over large areas. And here's an example. This is in Yakut. You have detectors separated by 450 meters. This is quite serious, covering 12 square kilometers. And so, okay, I don't go into the details. And the idea is that from time to time, a huge cosmic air shower arrives, and you would trigger several detectors like that and try to understand the energy. Okay, another array like that in the UK. This one is in New Mexico. Oops, sorry, this is French again. You see John Linsley, a famous colleague of Luke, probably. I have met him a few times, but you must have known him. Yeah. So he's chasing some snakes here. But anyway, from this detector, a very, this and a few others, a very, very high energy cosmic ray has been observed on February 1962. A cosmic ray with an energy larger than 10 to the 20 electron volts. That's 100 billion of the energy of normal light. That's just absolutely crazy. And if you think in terms of Lorentz factor, this is Lorentz factor of 100 billion and 100 billion, yes. And this is the velocity compared to the speed of light. This is not 1 time, but quite close to it, right? And with this relativistic factor, which is just a measurement of the effect, 1 second of proper time of these particles is 3,500 years of our time. And the distance from Earth to the Sun, 150 million kilometers, is just 1.5 meters. This in the race frame of this particle. The distance from the Sun to Earth. This is just crazy. Actually, this energy is macroscopic energy. It's the energy. I mean, it's joules. It's one particle, one nucleus, which has macroscopic energy. There's another technique to detect these particles, which is called the fluorescence technique. It's very easy to understand. If you have ever seen northern light, if not, you're not lucky. But if you have, it's really fantastic. But anyway, you must have seen some pictures. So what occurs that you have energetic electrons guided towards the poles, essentially, and they would excite the molecules in the atmosphere. And when they de-excite these molecules, they emit some radiation, fluorescence radiation, as we call it. And so the point is that the particle shower produced by these very, very, very high energy particles from space is so large, one particle with this energy, the highest one, will produce 100 billion secondary particles. So many particles which can excite the air, just nowhere around. And then the air will de-excite, emitting fluorescence. Of course, all this is created by one particle. So if you want to see this light, you have to be in very dark night, no moon, very far away from city light. But you can actually see the light produced by the secondary excitation of the air coming from one cosmic ray from space. And so if you look hard enough, you will see this. So this is a detector in Utah which has been set up to observe the sky at night, at moonless night, to see the track of the cosmic rays by the fluorescence light crossing the field of view, crossing the atmosphere at the speed of light. And indeed, it works. It just works. You can see the light, well, with some detectors. It's mostly UV, ultraviolet light, so you don't see by eye, but anyway. And on these dates, the highest energy cosmic ray ever had been recorded, to date at least, 3.2 10 to 20 electron volts. That's the energy of a tennis ball at 150 kilometers per hour. This is just huge, okay? So that definitely keeps alive the dream of cosmic ray astronomy, because these particles should not be deflected too much by the magnetic fields, right? And so they should point towards their source. At least that's the hope. Of course, this dream has a cost. These particles are extremely rare. And, okay, this is the most beautiful picture I will show tonight. Are you ready? Yes! Fantastic, no? Okay, let me explain that. Okay, this is just the flux, the number of cosmic rays you get every second, as a function of energy. What is amazing here, so you see that at low energy, you have many, many particles, and the higher you go in energy, the fewer they are. Now, to give you a sense of how little they are, I have to put numbers on that. So, actually, this is more, I put the same scales, and then you see that it's really steeply falling down. The flux is really decreasing very fast. It's very impressive. It's really one of 7 wonders of physical world. I would put it among the top 3, maybe top 2, 1. Well, it's an impressive regularity, which means, so if we call that non-thermal spectrum, it means it's completely out of equilibrium. If you generate a distribution of energy of the particles like that in the cosmos and you let it go, it will quickly relax, lose energy, and relax to almost only low energy. So it means you have to produce this spectrum over and over again. This is extremely irregular, over 12 orders of magnitude in energy, which 12 orders of magnitude is the same ratio as between thickness of a hair and 100,000 kilometers. This is a huge range of energy, and you have a very consistent phenomenon which has to be done all the time by something in the universe to refabricate this all the time. And the flux level extends over 32 orders of magnitude, which is the same ratio, sorry for the N, as between the thickness of a hair and 10 billion light years, which is just the size of the universe. So you have an extraordinarily regular phenomenon which is there, and okay, we would like to know what produces this. That's quite obvious as a question, no? Anyway, what about the numbers of the flux? So about this energy, you have 1 particle per square meter per second. So you have a detector of 1 square meter, it comes 1 every second. Fine. At this energy here, 1 particle per square meter per year. And at the very highest energies, 1 particle per square meter per billion years. So if you have a detector of 1 square meter, you have to wait for 1 billion years to get 1. And we want to do science with that, because those ones are the ones which are interesting. They are the ones which should go straight and tell us where the sources are, at least the sources of these ones. So obviously you need huge detectors. So I will go quick on that. So one of these, well, the biggest detector to date is in Argentina. It's called the Pierre Auger Observatory, as a tribute to Pierre Auger, who discovered these showers, thanks to which we know that these particles exist and we can actually detect them. So this is in the Andes in Argentina. I've been lucky enough to spend 10 years, not there, but going quite many times, but I mean to spend 10 years in this big international collaboration. So this is almost on scale, well, a bit larger. So it's a significant, 3,000 square kilometers is quite big. Did I say already 3,000? It's written there. Yeah, it's a 3,000. So this is a map. So there are 1,600 detectors covering empty land, essentially, in the plateau in the Andes, and which at night is very, very dark, and you can see the tracks of the cosmic ray showers. So I won't go in the detail of the detection. It's not, but just to give you an idea. So this is one of the detectors, another one. This is zoom. The distance between two detectors is 1.5 kilometers. When you sit here, actually, and you look for the next one, it's very, very, very far away. And when you think that some of these showers generated by one cosmic ray, creating secondary particles, can hit up to 60 of these tanks, covering a huge area on the ground, it's absolutely amazing. One cosmic ray with huge energy can trigger such a huge shower of particles which would go to the ground over a very big surface. It's really fascinating. Anyway, but you need these large surfaces because the particles are so rare. So blah, 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 blah. Okay, very quickly, the results. I won't show very much scientific results, just some idea. Of course, we made important progress from this detector, but one thing very important, we discovered that the highest energy particles are probably not protons, actually, which are the most common nuclei in the universe, but the highest energy particles seems to be heavier than that, and possibly the highest energy ones are actually iron nuclei, which is bad news somehow, because iron nuclei have more charge than protons. They would be more deflected by the magnetic field, so you would need even larger energies to really start to do astronomy with these particles. But anyway, this is what we have, and this is nature. So maybe that's the reason why we could not yet identify individual sources just by seeing accumulations of cosmic rays coming from a given point, which would then be the source. So the magnetic mist is not yet broken, but it seems to start to be broken. Notably in the northern hemisphere, there's another detector which seems to start to see some accumulation, which is quite interesting. So this was a surprise. We hoped, obviously, to see sources. We were not yet there, but anyway. But it's also a challenge. It means we should go to even higher energy or to observe with even more, observe bigger volume of atmosphere. So the idea is that would be to go bigger. We know we have to. Pierre Auger Observatory is simply not big enough. But when you see that, and when you've been working on this, you really realize you cannot go much bigger on the ground. There's just nothing. You cannot cover. We tried to cover 20,000 kilometers in the north, but it's just essentially impossible for practical reasons. Money, but also just to do it. I mean, you have to, just to maintain such a site, it's just impossible. So the idea to go beyond, well, it's given by this picture. Why not simply go to space and look down to the atmosphere from space? Because from space you are quite far away. So this is the concept of GEM-USO. It's crazy dream maybe. USO means Extreme Universe Space Observatory. So it's an observatory in space that will observe the extreme universe. The extreme universe are these particles, obviously. The idea is very simple. You go far away, you go essentially on the space station, 400 kilometers above the ground, and you observe over a wide field of view plus or minus 30 degrees like that. And whenever a high energy cosmic ray crosses the atmosphere, it would produce this fluorescence light, which I mentioned, and you would just see it. You would see the track. But the idea is that since you are very far away, you cover a huge volume of atmosphere. Where is it? Here. You cover almost 200,000 kilometers on the ground at once. This is our dream. Okay, actually, this instrument should be installed on the Japanese module of the space station, which is called Kibo, which means hope in Japanese, so it's probably appropriate. And JEM means Japanese Experiment Module. So it should be somewhere here or here. Anyway, so I think I'm getting towards the end. So let me just to give you an idea. So this is the field of view over Japan in that case. Because, the field of view of the instrument on the space station. Of course, it will cover the whole Earth, but to give you an idea of the size. And then you can even tilt the instrument so that you cover an even larger fraction of the atmosphere. Oops, I thought I had this one. I don't. Anyway. Okay, so before that big dream, there has been an intermediate step 3 months ago. Well, it took 2-3 years to develop, but the flight took place 3 months ago. It's called User Balloon. This is a CNES mission, the French space agency. And it's conceived as a pathfinder to GEMUSO to demonstrate the technology, to show that we can actually measure the fluorescence light of these showers from space, and to do some measurement of the background, but various things which are interesting for preparing this big mission whenever we will get the funds for that. And since this balloon is too small to actually see the cosmic rays, which are too rare, because it has flown only for one night, so if one night of a small detector was enough, it would be known we would not need this huge thing. So, so we could not see a cosmic ray, so we thought we would make fake events. So the idea is that we had lasers to shoot laser beams that we would observe as if it were a cosmic ray track. Okay, it was an idea to compensate for the lack of. So, okay, I don't go into the details. This is the instrument that we developed with many contributing countries. Oh, this is a bit funny. We use the Fresnel optics. You want a large field of view, okay, to cover a large atmosphere, and you do that with these kind of lenses, which you maybe find at the rear of the buses. I don't know here or well. Anyway, okay, that's just funny. The GEMUSO instrument, the user balloon instrument was integrated, and the flight so it was ready for the flight. So this is us 3 months ago in Canada, in Timmins, in the Ontario province. And then we were, okay, we need a little bit of video. So the idea is to go to 40 kilometers altitude and look down. So this is something I did not point out, but you see what it means. We want to go in space to look down to Earth, but to see things coming from space. Usually you go to space to look at space. No, we look down. So we want to go with this balloon. We actually went to 40 kilometers altitude, looking down to the ground to see the background and to see these artificial events. I tried to see the artificial events, the laser shots that we shot. And so this was time for the flight. Maybe it's time for me to show just the movie, and then I will quickly finish. I have essentially 3 or 4 slides. So some of you saw the movie of the inflation while just before I won't show it all again. So these are huge balloons which go to 40 kilometers. It's really, when it's inflated over there, it's, oh yes, there's a comment I want to make though. The payload is, you don't see it here, is 500 kilos. The balloon, all this, so this is just to put helium in the balloon. This is the balloon which is going to be inflated, and the balloon is all this, and all this, and all this, and all this is the balloon up to over there. And because when it rises, it will be bigger and bigger because the air is thinner and thinner, and so you need bigger volume to just be able to hold compensate for gravity. So you see, helium is going in there. So it's very delicate things. Launching such balloons is really something very, very difficult. Only a few teams over the world, few agencies can do that. And this was a collaboration between French agency and Canadian Space Agency. So, okay, it's no need to go much further, but I wanted really to show you the size of the balloon, which at the pressure, atmospheric pressure, will be small even during the launch, but then will grow up to 100 meters diameter. So that's a football field on 3 dimensions. That's just absolutely huge. That's why you need a lot of helium. So this is how it goes. It's quite beautiful to see, actually. So the guy is holding his weight, and at some point he will let it go. It has to be very, should not make knots and things like that. So it's up, and then it goes, and so on and so on. Okay, and then, oops. Just let me show you the actual launch. That was so moving to see, as you can imagine, for all of us who had worked for some years on that. So, it's gone. You see this very beautiful shape. And then I will show you where the payload. So you see it's almost not inflated, but it's enough. So the payload is actually here. Well, here. So it goes in. This is all the flight instruments, and then look at the acceleration. This is 500 kilos, and here it is. Go! When you see that by your eyes, it's really, really fascinating. This thing that you've been working on, and suddenly. So it was really nice. Everything worked well. We had exactly the conditions we wanted. There was some fear that because the balloon actually landed in the middle of the lake, and we were quite afraid of losing the data and so on. But okay, we had sort of put in floaters, and they did float, so it was okay. Okay, so enough of this. So let me just essentially finish. So I show you just out of emotion the first light that we were able to see. So this is the focal surface. So each of these pixels is actually sensitive to single photon. We can detect single photons. So and what we see here is it's looping, but it's the city light when the balloon is ascending, and you see the oscillation of the balloon. So at least we knew that the balloon was, but the instrument was working and recording data. And then the first event, this was maybe 1.5 hours after we started the operation. It was very moving. So you see obviously some light crossing the field of view, and each image is a 2.5 microseconds. We take 400,000 images per second. And when you know the sign of the field of view, and you can compute the velocity of the scene, and if you do the length divided by the time, you'll find exactly the speed of light. This is the laser, so we have a measurement of the speed of light. This is the laser beam. We did see the track. It was made for that, for us to see fake events, but we did see it. It was very, very nice. So, well, this is just a scheme showing that, because we went with an helicopter below. This is the track of the helicopter below the balloon to shoot the laser from the helicopter, so that we could see these events. Of course, quite nice. So the data are being analyzed now. So this is the kind of thing we are looking for. This is this does not speak much to you, but look at this excess light that you see here, and then the next 2.5 microseconds, it's moved and moved and moved and moved and moved, and this is really the tracks that we are looking for, and we can analyze that and do a lot of things, but this is just work beginning. So that's essentially the end. Let me just conclude. So much more is to come. We are looking now for a second flight, which would be a long duration flight of several weeks, not just one night, with the goal of really seeing real events, real showers from space. And probably that will be from New Zealand, operated by NASA, with also participation of CNES and other agencies, and Japanese and Italians. Okay. And then there is a new, sorry for the N again, a new Pathfinder, which is called Mini-USO, which is essentially the same instrument as we flew on the balloon, but which will go in the space station inside to look from the space really to the background. Then there's another mission called Klidve by the Russians. Maybe you don't care too much about that, with participation of JAXA and the GEMUSO collaboration, which I'm happy to be part of. So the quest is long, but the quest is still alive. That's the point. So let me summarize. Cosmic rays have raised many questions since 100 years, the main of which is obviously where did they come from, which we still don't know. Today, okay, this is, okay. I had no time to emphasize that or demonstrate that, but keep in mind that they play a very central role in most of the major processes that occur in the galaxy. This goes from heating and ionization of the interstellar medium to equilibrium between different gas phases, the control of astrochemistry, generation of magnetic field, star formation regulation, nucleosynthesis of light elements. Remember these nice things here. They also carry information about fundamental physics problems, especially the very high energy cosmic rays. Keep in mind that the most energetic particles that we have discovered from space are 10 million times larger in energy than the highest energy particles that man has ever been able to produce. Of course, we don't control the beam, so it's not easy to do physics with that, but still, there's potential here. So, and also remember, cosmic rays convey new types of messengers that we just want to decipher, to do really a parallel or complementary astronomy, not just with photons, but with these new messengers, which are cosmic rays. So, ultra-energy cosmic rays are very special. I showed you that. They have a huge energy. It's a deep mystery. Nobody knows what in the universe can produce them, accelerate particles to such high energies. And so, the potential for discovery is large. As I said, there might happen a new astronomy based not on photons but on nuclei, really matter from other galaxies in that case. Okay, some say we're crazy because this particle is simply too rare and it's too hard to catch and so on and so on. And it's not even clear we will learn so much. Maybe the message you have to tell us is not so important, who knows? But okay, I like this quote by Michelangelo. I don't know if the translation is correct, but it's better to aim high and miss the target than to aim low and actually reach it. I really like it. So please stay tuned and go Rev Magat.